The event-driven architecture or EDA pattern is taking center stage in modern software design. With the rise of microservices, big data and real-time processing, companies need scalable and flexible way to handle interactions between different components. In today's video, we'll break down the event-driven architecture pattern, explore why it is gaining popularity and dive into real-world case studies of companies like Netflix and Uber, who are leading the way in using this architecture to handle billions of events daily. Let's jump right in. As your application expands and new services are introduced, the traditional request-response model becomes less efficient. In a simple case, Service A requests data from Service B, which processes the request and sends a response. However, as more services are introduced, managing these interactions become exponentially complex. Consider this: for every interaction, you need to define a request and response. When there are only few services, this may seem manageable, but as more services are added, the web of connections quickly spirals out of control. Each service must be aware of and capable of handling requests from multiple other services, and this leads to tightly coupled interactions, making the system difficult to scale and evolve. Introducing or updating a service can disrupt the entire network of connections. This is where event-driven architecture comes into play. EDA offers a streamlined alternative by decoupling services through the use of events, allowing for more scalable, flexible, and efficient system designs. At its core, an event-driven architecture is a software design pattern where services communicate through the generation, propagation, and consumption of events. An event is simply a signal that something significant has happened, whether it's a user clicking a button, a new order being placed, or a device sending data. In EDA, instead of services calling each other directly, they respond to events, making it easier to scale, decouple components, and handle real-time data efficiently. And there are two main components in event-driven architecture. Event producers are the components or services that generate events. For instance, in an e-commerce application, the order service can be an event producer. When a new order is placed, it produces an event like order placed or payment completed. Event consumers are the components that respond to events. In our example, the inventory service might consume the order placed event to reduce the stock of items, while the shipping service might consume the event to start processing the shipment. This model completely decouples the producer and the consumer. They don't need to know about each other. As long as they are connected through a common messaging infrastructure, they can communicate via events. As one of the largest media streaming platforms, Netflix handles over 1 billion events each day. The platform uses event-driven architecture to manage multiple operations from streaming data analytics to recommendations and error handling. And here is how Netflix utilizes EDA. Every action you take on Netflix, whether it is starting a new show, rating a movie, or pausing a stream, it produces an event. This information is gathered in real time and sent to different services, like the recommendation engine. For instance, if you start watching a new show, that event is immediately consumed by the recommendation service, which updates your list with similar content you might enjoy. Netflix's architecture continuously monitors every service's health. If a service starts to slow down or fails, events are generated and the monitoring service consumes those events to alert engineers or trigger automatic recovery processes. By using EDA, Netflix can handle massive amounts of real-time data, scale its services independently, and ensure users receive personalized recommendation instantly, all without tightly coupling services. And similarly, Uber operates on a massive scale, handling millions of rides across the globe every day. Uber uses an event-driven architecture to manage both real-time data processing and coordination between services. Here is how. So when a user requests a ride, an event like ride requested is produced. This event is consumed by multiple services. So matching service finds an available drivers based on the user's location. An ETA service estimates the time of arrival. The pricing service calculates the ride cost based on factors like distance and demand. And each of these services consumes the same ride requested event but responds in a different way. Uber also has the ability to collect real-time traffic data through telemetry events from drivers' phones. This data is consumed by the routing service, which provides optimized routes and updates driver apps in real time. Uber's EDA allows the platform to process high-frequency events like ride requested, location updates, and pricing changes with high efficiency and fault tolerance. Now, recently I have explained the concept of service mesh and sidecar pattern. Event-driven architecture, service mesh, and the sidecar pattern are all patterns used in microservices architecture, but they solve different problems. EDA is all about event-based asynchronous communication, whereas service mesh deals with managing synchronous communication between services. In systems where both event-driven and synchronous communication are needed, the two patterns in fact can work together. For example, synchronous API calls between services can be managed by the service mesh, while event-driven communication flows asynchronously. Service mesh builds on the sidecar pattern by utilizing sidecars or proxies to manage network traffic between microservices. So, Netflix uses EDA to manage real-time user events like watching, pausing, or rating content. These events trigger multiple downstream services asynchronously, such as recommendation engines or analytics systems. While event-driven communication is asynchronous, Netflix still needs synchronous service-to-service communication for real-time decisions, such as fetching data from its catalog service or streaming services. A service mesh would manage these synchronous calls, ensuring that the retries, load balancing, and traffic routing are handled transparently. And each microservice in Netflix's architecture has a sidecar proxy, which might manage tasks like encryption for securing data streams, logging user events, and service discovery to ensure the right services are talking to each other. Scalability is one of the primary reasons companies adopt event-driven architecture. Since producers and consumers are decoupled, services can scale independently, and this makes it easier to handle spikes in traffic or workload. Now, there are two main styles of EDA: simple event processing and complex event processing. In simple event processing, an event triggers a simple reaction. For example, an order-placed event triggers the inventory service to update stock and the shipping service to prepare an order. This is straightforward and easy to implement. In more advanced scenarios, multiple events are aggregated and analyzed to detect patterns or trends. For example, Uber's pricing system might look at traffic, demand, and driver availability to trigger surge pricing. And this style allows for more advanced decision making based on event data. When designing an event-driven system, there are few components that are crucial. Event producers are the microservices or systems that generate events. An event could represent something like user action, for example a purchase, or a system change, for example a data update. Event broker like Kafka, RabbitMQ, or Azure Service Bus sits between the producers and consumers. It acts as an intermediary that handles events by either queuing or streaming them. Producers send events to the broker and the broker forwards these events to consumers. Some systems might have both publisher and subscribers. The publisher sends events and the subscriber receives events from the event broker in a pub-sub model. And this ensures asynchronous communication between services. Event consumers are services or systems that consume the event. They can trigger various actions such as storing data in a database, saving to a file system, or interacting with different applications. You also need to define clear event types and contracts so that consumers know how to process each event. For instance, an order-placed event might include fields like order ID, product details, and payment status. We will do a deep dive on various event types and contracts in my future video. Now, while EDA provides many benefits, it also comes with challenges. In large systems, ensuring events are processed in the correct order can be difficult. And since events can be reprocessed in case of failure, you must ensure that actions like detecting stock or processing payments aren't performed multiple times. Furthermore, managing eventual consistency across multiple services requires careful planning and design, as real-time event processing doesn't always guarantee immediate consistency. Finally, there are several tools available for building an event-driven system. Apache Kafka is a highly scalable messaging platform widely used for real-time data streaming and event-driven systems. Companies like LinkedIn and Uber uses Kafka to handle millions of events per second. Amazon's cloud-based messaging services are ideal for event-driven architecture built on AWS. RabbitMQ is another lightweight messaging broker that is easy to set up and use for smaller-scale event-driven systems. These tools make it easier to implement event-driven architectures that can scale and handle real-time processing efficiently. As we have seen with Netflix and Uber, EDA is more than just a trend. It's the backbone of systems that handle billions of events every day.